16. Oscillating Systems, Part 5. Energy in Simple Harmonic Motion. 1. Energy in springs. Energy is first supplied to the spring by pulling on a mass to extend the spring. So the spring has been extended from this neutral position to here. The initial extension will be the amplitude of the simple harmonic motion. So from there to there, that's the extension, and that becomes the amplitude once the mass starts to oscillate up and down. During oscillation, the energy changes will be between the elastic potential energy of the spring when it's stretched and the kinetic energy of the mass. The total energy is the energy stored in the spring when it was initially extended by the amplitude of the simple harmonic motion. So this A here, the extension is simply the amplitude there. At any instant, the total energy is made up of the kinetic energy and the elastic energy. So that's the total energy initially given to the spring system. Consists of the sum of the kinetic energy and the elastic potential energy. This table describes all the changes that happen to the spring system as a mass goes through this complete cycle. Look at this one here at the start. At the start, time equals 0, the displacement is maximum from this dotted line to that dotted line, stretched from there to there. Velocity is 0, not moving, but acceleration is maximum towards back that way. Kinetic energy 0 because velocity is 0. And all the energy is in the form of potential elastic energy. And as it goes from there to the equilibrium position, after a quarter of a cycle, the displacement is 0, not stretched at all, but the velocity is at its maximum, moving fastest. Acceleration is 0, and kinetic energy is at its maximum, and no elastic energy, and so on. Here we have a spring and mass system that has a spring constant of 110, and the initial extension, which becomes the amplitude of the oscillation, is 25 centimeters. You are asked to calculate the total energy of the system and also the kinetic energy of the mass when its displacement is 15 centimeters. For question A, straightforward, using that formula, you get the answer 3.4 joules. For question B, you had to first of all calculate the elastic energy when the extension or the displacement is that much. So the elastic energy is that much. Take that away from the total energy, what's left is the kinetic energy. Energy in pendulums. Energy is first supplied to the pendulum by pulling the bulb to one side. And when the bulb is released, its motion will be very close to simple harmonic motion, provided the angle is small. The initial displacement of the bulb will be the amplitude of the simple harmonic motion. The initial gravitational potential energy of the bulb is the total energy of the system, given by this mgh. You're all familiar with that. At any instant, the total energy is the sum of the kinetic energy and the gravitational potential energy of the bulb. So kinetic plus potential will give you the total energy. Here is a simple pendulum. Initially, the bulb is pulled to one side and thereby gains this height here, h. And therefore the gain in potential energy is mgh. And there is no kinetic energy because it's not moving. Upon release, it will swing from that position to that position. When it gets there, the potential energy is 0, or change into kinetics, or kinetics maximum. and as it swings towards the other side, the reverse happens. It goes back to that position. Here is a fairly straightforward example on simple pendulum that you can read through yourself and analyze the answers. Here is another example on simple pendulum, and it's a bit more involved. You have to calculate the angular frequency, omega. It's a hint here. And the maximum speed of the bulb and the maximum kinetic energy of the bulb. Work through the answers yourself carefully. Graph of energies versus displacement for a system in simple harmonic motion. You can see that when potential energy is maximum, kinetic energy is zero, and vice versa. When kinetic is maximum, potential is zero, but the total energy in the system is constant. This graph is more of the same, showing the constant exchanges between potential and kinetic, while the total energy stay the same.